So we looked at some animations of the Hadley cell, the ITCZ, the pressures changing with seasons and so on. And just to get more into why precipitation is so different and so much more challenging for observing and modeling, let's look at this ITCZ during the northern hemisphere summer when the sun is north, land is heating, ocean is warmer, so the entire ITCZ has been dragged, and the monsoon creates a special situation where the intertropical convergence zone is dragged much further north than anywhere else. And similarly, in our winter when the sun is south, the Amazon rainfall and the African rainfall drag the ITCZ much further south. ITCZ here gets a bit more complicated, which we don't have to worry about right now. So essentially, you can think of precipitation as a result of some instabilities or the buildup of moisture and something called available potential energy, or APE, or often called CAPE, or convective available potential energy, and so on. Very technical details, but the simplest way to think about it is like a popcorn kettle. You are heating the kettle, the temperature is essentially uniform over the whole kettle, and the kernels are sitting there and they will begin to pop, and you cannot always predict which one will pop next. So there is small differences in the area of the kernel getting heated, or the different small differences and so on. So the popcorn will just pop randomly here and there. That's essentially what happens. If we look at the temperature map, temperatures will be uniform over large regions. So if you think about temperature over the city you are in, the entire city may be very big and all the city will be at very similar temperatures, but rainfall may happen in one part of the city and not in another. Or even if you are in a rural area, the entire region may be having similar temperatures, but even clouds may be covering the whole region, but rainfall may happen just locally. So even though you have been showing the ITCs as a long band, if you look carefully at the image of the satellite for the ITCZ, you can see that there is clearly the structure of the ITCZ that can be seen, but within the ITCZ you have these lots of broken up pieces. So within the ITCZ itself there are popcorns of convection and rainfall happening. This is what makes it so much more difficult. It's a very nonlinear process, can grow very rapidly. So you can imagine rainfall during the monsoon. It's very warm, humid, and suddenly the rain will start without any warning. So this is the situation. So if we go back then and try to look at how the trends in annual precipitation have occurred over the time period of 1901 to 2005, there are later maps available now, but the point will remain the same. And if you look at different regions, there are different estimates of rainfall here as well as we saw before, and they all have fairly close variability or anomalies over time. But you can see that there are times when here the magenta line is actually on the negative side and the black line is actually on the positive side. So there are many such situations. So here this is going this way and the magenta line has gone this way. So depending on where you are, you can have differences in the observed rainfall itself. So why is that? Because whether you are using satellites or rain gauges or some other method to estimate rainfalls, the satellite cannot necessarily always see these popcorns. So it also can give different estimates because of different people doing the processing slightly differently. Or if you have rain gauges, the rain gauge is measuring at one location and it could be raining just 100 feet away and the rain gauge may not record it, or it could be a kilometer away and not record it, and so on and so forth. The other general principle to remember is that where there is high rainfall, like let's say coastal India like Kerala and Maharashtra, let's say Mumbai, when you have a high amount of rainfall, the variability will be generally not very high. Whereas if you go to a relatively less rainfall area like Rajasthan or Marathwada or Vidarbha or North Karnataka, the variability will be very high. So, it might rain 200 millimeters per year, but the variability can be 400 to 100. And so, when you look at rainfall, you have to look at the amount of rain, number of rainy days, and how long it rains or how often it rains. So, all these things are changing with warming. So, not only do they change with season, but as you change the background state and you change the instabilities that build up in the atmosphere and you change the way it rains. So, we will see more and more what are called extreme events, and I think if you look carefully or if you remember your own experiences or parts of India, there are huge floods in one place and there are droughts in another place. So, the distribution of rainfall is becoming more extreme, which means if you had an onset of monsoon in end of May, early June, and the withdrawal of the monsoon in mid September, now both have changed and you are squeezing them and you are distributing the rainfall differently. So, we will come back and look at more details like that. Okay. So, before that, let us go back to look at temperature. So, one thing we can say with high confidence based on observations is that the cold nights are generally declining, means there are fewer and fewer cold nights per decade. So, you can see that most of the colors are in this range, which means number of cold nights are decreasing, number of warm nights on the other hand are increasing. This is what global warming can be expected to do. The number of cold days also generally decreasing or not changing that much, whereas warm days are increasing quite a bit. So, India is now beginning to have lots of warm nights and warm days. For example, before the monsoon, especially March, April, May, almost every year we are having heat waves and hundreds and sometimes several thousand people die because they are out working in the field preparing land for agriculture before the monsoon, or they don't have AC and so on and so forth. And even if the predictions of heat waves is improving because the India Meteorology Department is doing a good job, you cannot move people from one village to another or cannot provide air conditioning and so on. So, these are the things we have to worry about. So, you can again see that there are large scale changes, whereas when you look at rainfall changes, generally they tend to be much smaller scale changes. So, it is called the decorrelation scale. So, if you take rainfall here and correlate with rainfall around, it will be only correlated on a small scale, whereas if you do the same for temperature, it will have correlations over a much larger scale. So, those decorrelation scales are much larger for temperature and much smaller for precipitation or rainfall. So, how do we know how the extremes are changing? So, extremes are themselves defined in different ways. This is something called 95th percentile. So, if you take rainfall distribution over, let us say, the monsoon season or on a given day, and you can look at 100 years of rainfall on, let us say, August 15th, and then you know what is the average amount of rainfall you expect, what is the typical maximum you get and the minimum you get, but sometimes you get very high amounts of rain. So, those are spread into percentiles. So, 95th percentile is like the top amount of rain you get in August, which is very rare. How are they changing? So, you can see that there are lots of regions, especially over India, where you are increasing 95th percentile in some regions like the northeast, where you are having a lot of floods, in the coastal and peninsular regions and maybe even in Rajasthan, whereas in central India or the Gangetic plain, you are having reduced amounts of extreme rains or 95th percentile. So, look at that figure again clearly, and this is how rainfall works. It keeps changing. So, if you rain more in one place, oftentimes you are taking the moisture from somewhere else. So, it automatically turns out that if you rain more in the northeast, for example, you will be taking the moisture from the rainfall that should fall on the Gangetic plain and vice versa. Okay. So, this is the second way of looking at it, where you are looking at daily precipitation intensity, which is also changing. So, let us just focus on India. We will come back to it, but obviously there are other regions as well. And in general, the southern hemisphere, there is a problem of data itself. So the amount of data available itself is lower in the southern hemisphere. In general, population and interest in meteorology has been much higher here. With satellite data, we are getting the coverage to be uniform everywhere, but before that, the coverage was very different. So that also is showing changes. Wherever you have these plus signs, there you do something called a statistical significance test. So if you're seeing a change, is the change statistically significant? It's a technical term, but if you don't know it, you can just read up on it to see that. That means you can say with a confidence of more than 90% or 95% that this change is real. Okay, so not every change is real. So you can see that the change is shown as a map, but the statistical significance is valid only in certain places. That's something also to be kept in mind. Looking at the another way, frequency of annual maximum number of consecutive dry days. So that corresponds to this. So where you have changes in extreme rainfall, you are also having changes in dry days, because as I said, you are redistributing moisture, but you're also doing something else. So if you are getting on average, let's say 900 millimeters of rain in a particular part of India, that rain used to occur between June and September 15th, let's say, but now similar amount of rainfall can fall, but it will be distributed on fewer days than before. If you were getting average rainfall of 10 millimeters per day for 90 days, now you might be getting 30 millimeters per day on only 30 days. So you are changing the distribution of rainfall, which of course is bad news for agriculture, because the crop calendar and so on, when you sow, when you hope they will ripen, especially things like onions, if it rains at the wrong time, the onion can rot in the ground, or it can do other kinds of crop damage if it's heavy rainfall. So those things matter. So it's the not just the intensity, but how it's distributed, that also changes. So this is, which means the maximum number of consecutive dry days will also be responding. So you can see that wherever there is increased precipitation intensity, there is like an approximate reduction in consecutive dry days. So remember, monsoon comes as what are called active spells, and it will be raining for a few weeks. Then you will have what is called a break spell or a mini drought, where it will stop raining for a few days. So these kind of distributions are changing. Okay, so lots of very recent research is there, and I will address some of that when we look at the monsoon in a specific lecture. And all that rainfall results in what are called hydroclimatic or intensity. So they are like floods and droughts and so on. So that is like a multiplicative measure of the length of dry spell and precipitation intensity. So you can see that there are changes in, this is normalized, we won't go into the detail, but just remember that the rainfall intensity changes, distribution changes are going to appear as hydroclimatic intensity changes. So we will see more details on how floods over India are changing, for example, when we do the monsoon lecture. Okay, so again, look at all the spotty distributions. Okay, that's always something very typical of rainfall. So you expect that as warming happens, there will be more moisture in the atmosphere and instabilities may build, but the rainfall distribution changes, and the intensity, duration and frequency also change. So this is now the measurements of ground temperature. These are typically what are called borehole ground temperatures. So the small narrow hole deep into the ground, and at the bottom of the borehole the temperature corresponds to the geothermal heating, and the profile of the temperature within the borehole close to the surface begins to show the impact of warming, how far down the warming penetrates into the borehole, because the borehole should be essentially protected from changes in the surface, but slowly, if warming is happening over time scales, then that heat will slowly begin to diffuse into the borehole and show up as warming temperatures. So this is now showing trends and model simulations based on the borehole temperature kind of data in degree kelvins per century, 100 years. And essentially the message is that over time every continent is essentially warming significantly. Okay, so starting from 1500 to 2000, every single continent is headed to warming. So it's not just the ocean that we looked at, it's not just the atmosphere that we looked at, even the ground is getting warmer and warmer, which is natural. And the biggest story is always, of course, glaciers and especially Arctic sea ice. And these are the regions where there are well recorded changes in the retreat of the mountain glaciers. Remember, the mountain peak is covered with snow and ice, and in cold temperatures that glacier extends down. Vegetation changes we looked at before showed that vegetation climbs up and climbs down with the cold periods. So with global warming, this glacier line begins to retreat. So that's what is a retreating mountain glacier is. And the Himalayan region, the East African Kilimanjaro highlands and so on, the Alps, the European, so this is the Alps, this is some other Eurasian mountains. Everywhere you look, Iceland and North America and South America, Andes, you have evidences of glaciers, mountain glaciers retreating. So the warming is going up, the lapse rate is changing, and tropopause height is increasing. But you have to be careful because the local dynamics, just like rainfall, glaciers are created by snowfall, which is also precipitation. When we say precipitation, it includes not just rainfall but also sleet, ice, hail and snow, right? So local dynamics can be very, very different. So this is typical example of complex situation occurs in the Himalayan region, where on the east side you have the influence of El Nino and the monsoon. So it depends on when it rains and how the accumulation of glaciers and melting of glaciers happens. In the central region you have again more the influence of the monsoon, whereas as you go far into the west, the snowfall is actually coming from the Atlantic in what are called westerly disturbances, which means those are more winter snow kind of regions rather than the monsoon time scale precipitation, snowfall or rain. So these are what are called more alpine, which means the winter melt and winter building is more like alpine glaciers in the Alps, whereas these are more impacted by other processes. And it turns out that because of the warming and local circulation, some regions of the Karakoram, for example, are actually not losing glaciers and may even be gaining, or they are in balance. What does in balance mean? When we look at glaciers, we typically looked before at accumulation, where the snowfall is accumulating and the glacier is growing, and ablation, where the glacier was melting and losing mass. So when we do mass budget, we always try to see what is the net accumulation, what is the net ablation, and together are they resulting in a growing glacier or is the glacier retreating. So this is just to point out that the combination of climates and altitudes and seasonality can create changes in a region that are much more complicated. So models right now are in fact not very good at doing this, and there were some misleading statements made in 2006, 2007 by the IPCC, and then they had to go back and retract the statements, and so we have to be always careful. So you can see that January is heavily impacting this region, whereas July is heavily impacting all these regions. So those kind of processes have to be kept in mind. Nonetheless, the Gangotri Glacier, which had reached down to this level in 1780, has been retreating almost constantly. So by 2001 it has retreated by something like 80 to 100 meters So this is a 1 kilometer here, so we have to be careful what is the scale. So there is a significant retreat of the Gangotri glaciers, and it also shows up in, for example, the growth of Glacier Lake. So this is the Toshorolpa Glacier Lake in Nepal. So it was pretty small in the 50s and kept growing and has constantly grown, and in 1997 in fact they had to drain the lake to avoid catastrophic flooding. So if the dam, the ice bridge broke and all the water got released, many villages in its path would be in danger. So actually had to drain it systematically to reduce the possibility of flooding. So even though there is complicated dynamics and some glaciers are gaining, the questions for Himalayas always is which glaciers are important for river flows, Indus, Ganga, Brahmaputra, and so on. Which ones are getting a lot of contribution from the glaciers, and what does it mean if those glaciers are disappearing or gaining mass? What does it mean for the hydrology and the water supply over India or Pakistan, Bangladesh, China, and Southeast Asia? Some of the rivers go all the way down into Southeast Asia from the Himalayas. And what does it mean for the conflicts? Because Indus River is shared by Pakistan, India, and Brahmaputra, Ganga shared by Bangladesh and India. Many states are sharing water and always fighting with each other. So as with global warming, you have to be very sure what this means. And when the government makes plans for connecting the rivers and making waters more available and more manageable, you have to be sure that you are actually moving water from a region that has more water to a region that is less water rather than the other way. So all those kinds of things are important when big plans are made. Anyway, to look again at the global mountain glacier stories, whether you look at the Europe, South America, the Arctic, Asia, USA, Alaska, and Patagonia, and so on, the cumulative mass specific balance, so how much mass is being accumulated or lost, you can see that some European glaciers were accumulating mass for some time and then they have started dropping again. The rest of them are all negative, which means they are all losing. The ablation is much larger than accumulation. Or you can also look at it as their contribution to sea level. Remember, any glacier that's on land, when it melts, that's the water that's going to be released to the ocean and the sea level can rise. So you can see that this scale is going down. So just to make it look similar, so the contribution in millimeters of sea level equivalent by the melting of the glaciers is also increasing correspondingly, and obviously this one looks different here than here because it depends on how big it is. So if it is a big glacier that's melting and releasing lots of water, it can result in larger contributions. So the Arctic, for example, has lots of sea ice. So obviously if it's already in the ocean, it doesn't contribute to sea level, but Arctic mountains also have mountain glaciers which can contribute to sea level rise. Okay. So Arctic, I think you've probably been looking at lots of news stories in on the Arctic, especially in 2006. I think the melting was so severe that you could directly go from the North Atlantic across the Arctic into the Pacific Ocean, the so-called Northwest Passage. So that would save you a lot of distance instead of going around South America and up into the Pacific on the other side, right? So the September ice extent in millions of kilometers square has been dropping fairly significantly. And why is September important? Because that's the end of the northern summer. Any ice that remains at that time can have high albedo, and during the winter it can accumulate snow and grow. So the extent of September ice is very critical. If the September ice is retreating very fast, that means the accumulation in winter is going to be reduced very fast as well. Okay? And just for being careful, whenever we look at data which is very short, like this is only about 30 years, 35, 40 years, then you have to always keep in mind that things like PDO, Pacific Decadal Oscillation, and North Atlantic Oscillation also have this 30-40 year time scales. So we have to be very confident that these are trends and not just part of the natural variability. So that is something that has to be constantly monitored. But when you combine with the radiative forcing and circulation changes, precipitation changes, and all the other evidences in sea level, humidity, growing season, which we will look at, and so on, it becomes a question of how do you assess risk. Do you want to assume that this is natural variability, or do you want to be careful and assume that this could be part of the global warming, right? Everything in life comes down to risk assessment, and it's clear that we have to be careful. So especially when you look at the changes in the volume of Arctic ice in every month, every single month has been dropping during that time. So that doesn't seem like natural variability, because natural variability is, remember, El Nino peaks in December, January, February, and not in other seasons. Similar things happen with other modes of natural variability. So you would expect, if it's natural variability, then maybe melting is more in the summer, but then winter is accumulating back up and down, and so on and so forth. But these are systematically dropping in each calendar month, which is most certainly, or in the best guess we can make on this time scales, is a fingerprint of human activity and increased global greenhouse gases and greenhouse warming. Okay. So this is the March April snow cover in the northern hemisphere, again dropping quite significantly. So this is unlike the glacial interglacial times. Just to return back to make the point, when glaciers were building, we said the snowfall rate drops because the global cooling happens, whereas here global warming is happening, but snow cover is decreasing because you are melting the snow, and oftentimes snow is falling as rain instead of as snow, which of course melts the snow that's already there. So we have to always keep in mind that we are now changing greenhouse gases, radiative forcing, and temperature is then responding. So unlike the orbital forcing glacial deglacial times, where temperature changes first and glacial melting happens, then carbon dioxide and methane respond, here we are doing things the other way. This matters for how processes work. Good news again, as we saw with data gathering in the ocean and the atmosphere and satellites and so on, the measurement of ice volume is getting more and more accurate. So as we go into the future, this data begins to build. So the evidence and the attribution, so detection and attribution, is going to get better and better, because even the models should get better and better over time. So these are now have radar and gravity measurements. Basically, gravity measurements means as the amount of mass, whether it's glacier mass or groundwater mass, locally stored changes, you can fly two satellites one behind the other. So they are coming from one gravity, take a dip if the gravity increases and go back, another one takes the dip. So together they can be used to infer the changes in the mass of either groundwater being extracted and distributed or glacier mass changing. So there is a mission called GRACE, Gravity Recovery and Climate Experiment, which has these two satellites flying very close to each other, so that they can closely track the gravity anomalies and infer the mass changes on a fast time scale, which typically comes from glacier mass changes or groundwater changes. So some remarkably new results came out of this mission, which related to mass changes in Greenland, and also groundwater changes over India, the Punjab region, for example, and so on. So we'll look at some groundwater changes as well as we go into the future. So Greenland is the other hot spot, as you can imagine, because we are in the warming phase. So ice albedo feedback can produce abrupt changes, and Greenland is sitting right there where the deep water formation happens. So it can have serious perturbation to the thermohaline circulation, and that can translate the perturbation to global scales through the global thermohaline circulation. So gigatons of mass loss in Greenland in recent years, again very short time scale, but nonetheless consistent with every other evidence, is a fairly significant drop. This is been observed a lot now. Lots of teams from all over the world are always on Greenland, living in very harsh conditions. And Greenland has been giving us new insights on many new processes. So typically, if you have thick glacier and somehow the warming and melting starts, it can create kind of a glacier lake lens of water on top, which will have much lower albedo than the ice around it, which means it will start absorbing more energy. So it will get warmer and it will start melting more. And soon the melting gets so serious that it begins to create these kind of waterfalls within the glacier, and it pours into the glacier and creates what are called moulins and so on. Moulin is like a French word, you can look it up. So they can go all the way to the bottom, the bedrock where the glacier is sitting, and they can begin to lubricate the bottom, which means the glacier movement can be accelerated and so on and so forth. So albedo changes, glacier movement changes, and so on. So Greenland has become a spot where lots of observations are being made and lots of new insights are being gathered. So this is showing over the same period changes in surface elevation. So glaciers are very thick, so you want to monitor the elevation change, but that doesn't necessarily mean that's the volume change. They are always struggling with making the mass estimates as well as elevations. Elevations are easier to track because the satellites or aircrafts can go and take measurements with lasers and radars and so on. And you can see that this is for 2003 to 6, 6 to 9, 9 to 12, and the yellow regions are basically where the elevation changes are negative, which means the glacier is dropping in height, and the green regions in the center is where the elevation is slightly positive, so accumulation is still happening and glacier is potentially still growing. The main message, of course, is that everywhere in the edges the elevation is dropping fairly significantly. There are some regional differences, but nonetheless you can see that there are large regions where the elevation rates are dropping at order 10 meters per year. That's a huge amount of loss of ice. And again, the albedo changes and the ice albedo changes, ice albedo feedbacks means we can have accelerating positive feedbacks. Not a good news. Antarctic, as we said, has had complex situation. We will see a map soon, but it has had these remarkably impressive carving of large ice sheets. So remember the mountains, the glacier flows, spreads onto the ocean, has a thick ice shelf which becomes susceptible because of the waves and the tides, and of course the warming, because the warm water coming in can release a lot of heat below and start melting. So the Larsen A and B were two big ice shelves, and the Larsen A ice shelf had a collapse event in 1995, and this is very well recorded Larsen B event that happened in 2002. So it had extended to here in 47, retreated a little in the 60s, went back in the 90s, kind of natural variability combined with some global warming already emerging. You can see that there was a dramatic retreat in 2002, and then it just broke off a huge chunk as large as the state of Rhode Island in the US, 220 meter thick ice shelf, area of 3,300 square kilometers, 3,250 or so, just broke off. That's massive loss. And the big impact of that will be that when this breaks off, this begins to create problems with the glacier that's behind where the grounding line is, whether that can slip more, the grounding line can shift, and so on. So the glacier dynamics can get fairly dramatically altered by removing the leading edge ice shelf at the leading edge. So this is never the good news. Okay. Just to re-emphasize the complexity of the Antarctic in terms of what we saw before, ocean is warming, air can warm and can hold more moisture and can create more snowfall potentially. but the ocean can also get under the ice shelf and begin to melt it faster and then create problems for the anchoring of the glacier and so on. So, this is showing striped regions where carving is happening, pieces are getting removed and melting is happening. So, you can see that there are basically all around various rates of, so this is showing the area, various rates of carving or melting happening all over Antarctica. But when you look at melt rates, there are regions where there are positive melt rates and there are regions where there are negative melt rates. So, obviously depending on which side of the wind the glacier is and how the mountain is creating rising air and snowfall and glacier growth or glacier melt accumulation versus ablation, you have fairly complicated situation. But nonetheless, this has been around for almost 35 million years, locks in huge amounts of fresh water and sea level rise. So, every time we think about large glaciers like Greenland and Antarctica, we also have to remember the equivalent sea level elevation, sea level rise that is locked up in those glaciers. That's something like 60 feet for Greenland, and I think it's more than 120 feet for Antarctica. So, you can look up those numbers. What are the other impacts? We'll keep on looking at many other impacts. So, this is something called permafrost. What does it mean? Basically, the air temperature is so low that the cold temperatures penetrate deep into the ground, and the top layer of the soil, I will show figure next, remains active in the summer months. It can get little bit melted and unfrozen. So, biology can happen and other things can happen, exchange of gases can happen, but below a certain depth the soil remains permanently frozen. That is what is called permafrost. So, these are the regions where, so this is the Greenland glacier, but around it you can see all these purple regions, including some just to the north of us. There is tons of permafrost regions. So, permafrost basically can have some sort of a vegetation like a tundra on top, and the active layer seasonally can melt and thaw, and below that active layer you have the permafrost region. So, as global warming happens, the heat keeps penetrating. So, the active layer gets deeper, that means the seasonal melting and refreezing begins to get deeper and deeper. But the bad news is that this permafrost has typically buried a lot of organic matter, methane, carbon dioxide locked into this frozen soil. As you begin to melt, that organic matter begins to thaw, and there are microbes and so on which can begin to respire it. So, it begins to decay, and you get potential for release of CO2 and methane, which can then have a positive feedback. So, there are various estimates of how much methane and CO2 is locked in there and what would happen if they begin to get released. But here is the data showing for the Canada region. You can see that the depth of the active layer in meters is increasing over the last several decades from the 1950s to 1990s, whereas the seasonal freeze depth is decreasing. So, cold winter should increase the freezing depth, and the summer should not get too deep in terms of active layer, but summer is getting more and more active, deeper and deeper, and the winter freezing is decreasing. So, it is a double whammy from both seasons creating problems. There are some complications. It turns out that some of the thawing of the permafrost is actually creating lakes, and those lakes are beginning to have some photosynthesis in them. So, they are beginning to sequester some carbon. So, it is possible that the release of carbon dioxide and methane from the permafrost may not be as severe as we thought, but we need to be carefully monitoring these, because if we made a judgment error on that, that could be not good news again. Okay. There is a much more subtle point involved in these snow melts, mountain glacier melts and so on. For rivers which get lots of water from snow melt in the mountain and glacier melt during seasons, this is showing water flow rates for a river in Austria, and you can see that in 1978 the river discharge used to have a seasonality but fairly mild. Okay. Typically there is an increase in what is called a spring discharge, but this is only showing summer months. But you can see that with global warming in 1998 we have massive changes. Hourly discharge rates have jumped up by several times because of this rapid freezing and melting cycles. This is got some subtle effects because where the river runs into the lake or the ocean, there are many living creatures like crabs, oysters, clams, fish, shrimp, groundfish, whatever. They all have evolved to time their breeding cycles so that larvae can have food when they are trying to grow up and so on, to when the spring melt happens and when the river discharge is maximum, when the organic matter is coming in and so on and so forth. But changing the river discharge this way is decimating many of those ecosystems. This is not something you would immediately think of. In addition to managing the resources, water resources, if you are a water manager and you are used to certain flow of river discharge, certain rates, obviously you have to be careful how it is changing. But these ecosystem responses are also very, very critical. So this we will look as we go more into this direction, we will see that there are what are called cascading feedbacks in the system. So we'll look at some examples from several continents on what kind of cascades are possible and what are being observed. So this is again perturbing the system somewhere. Everything is linked to everything else like dominoes, and the reactions continue through the system, and some of them we didn't even know, we didn't expect. But now when we want to deal with global warming and climate change, we have to be very careful to track what are those domino effects in the system. Okay. So we'll come back and see that next time. See you next time.